Okay, guys, welcome back. Hello again. Hope everyone's doing really good, and I'm just here to get us started. For the moment, we're waiting for 11:30, so we got about 3 more minutes. But thanks, everyone, for your time and your attention, and we'll be good to go in just a couple. Hi, Kalaya. Hi, Valeria. Oops, no, sorry. Hey, Jasmine, Samir. Glad to see everyone here. Good morning. Hello, Arlene, Rachel, everybody there. Hope you're having a great week so far, and that your classes are going well. Hi, Nathaniel, Josephine. It's always good to see you guys. Feel free to say hello. Hey, Brenna. All right, just another minute or so. Alrighty. Hey, Jamie. How's it going? Stephanie. All right, guys. Well, it's more or less time, 11:30, so I'm just going to go ahead and get us going. Thanks again for being here, and appreciate all the work you're doing this semester in my class and in all your other classes too. So let's just pick up where we left off. About the upcoming couple of meetings. So next Wednesday, a week from today, that's the day of the midterm, and over the weekend, between now and Monday, I'll send you guys a study guide, which will just give you a list of topics that you kind of want to brush up on and review to prepare for that test. So I think I'll send you that on Friday, and at that time I should be done with the grading of the second homework that everyone submitted. So I'll also post the answer key to the homework, and any student can definitely just get in touch with me for their score on that over the weekend. And when we return on Monday, we'll have that review session, go over the study guide, talk about the material again, and then we'll be fine and prepared for the Wednesday exam next week. So that's the next few dates. But today, we have a little more work to do on these truth tables. There's one last truth table analysis method that you have yet to learn. So that's the goal today. Well, there's two sort of major goals today. One is I want to do a few more practice problems on truth tables to evaluate whether a set of sentences is consistent. And then once we've, refreshed our memory and done some more of that, then I want to use the remaining time to talk about how truth tables can discover whether an argument is valid or invalid. Okay, so truth table material today on two topics, consistent set of sentences and validity and invalidity. And I see all you guys over here in the chat, so good to see you, Leo and Melanie, Ella, and everybody else. Okay, and as usual, as we've done throughout, when you have questions of any type, feel free to let me know in a chat or in whatever way, and I'll just take them as they come. Now, we've had the dual format method for a while, which I think is working pretty well because it allows us to archive the lecture. You can still see all the work on the board when you come back to the archived recorded versions on my YouTube channel. But it's also helpful, I think, to pull up the screen share function so that we can all see a clearly typed example that we're going to think about and work on. So as I've done a few times already, I'm going to just share to you the Zoom link, okay? And so I'm going to open this Zoom meeting, and I'm going to have both of them running at the same time. So switch to the Zoom if you can, and then any later time in the future, you can come back to this YouTube channel to view the lecture again. Okay. No, Eddie. Big boy. All right, everybody, here we are. So I'm just going to, sorry, Eddie. This guy's getting so big, almost 10 pounds now. It's growing right before your eyes. Okay, so I'm sharing the screen. So that's now displayed. And let me pull up the textbook here. Okay. All right, guys, so also, sorry, one moment. Let me get the chat in the screen here. I gotta be able to see your guys' comments. Okay. Anybody just type something in the chat just to make sure that everything's properly working and you can hear me? Okay, good. So everyone's able to hear me, no problem. Okay, thanks. So as we continue developing our understanding of truth tables, I wanted us to take a look at some of the problems here in the section 3.4. Okay, so let's try the problem here that you see, letter B. Okay. Now remember how truth table is to evaluate sets of sentences to discover whether consistent or not. You know, the first method, the first step in the method is to create this cross hash. Now in the top right, I'm looking at problem B here. You guys see that in the notes from the textbook. It's this little set of sentences. So we have three sentences. The first one says that B, if and only if both J and K sorry, no left-facing parentheses. This is enclosed in braces, so yeah. The second proposition is it is not the case that J, not J, tilde J. Sorry, I need to slide this over to the left just slightly to give myself a bit better ability to write. So do allow me that luxury. So B, really? Thought I had a very, very good marker, but we'll go with this red one. B, okay. Just a little moisture right there. That was causing the problem. Sorry. I need a more porous item really fast. All right, guys, thanks. Technical difficulty, huh? Okay. B, double arrow, both J and K. The second one, tilde J, not the case that J. And then the third one, if not B, then B. All right. So here are three propositions. And so the next step is just to ask, where will I place three downward-facing arrows? Because there have to be arrows placed above the main connective of every formula. So in the first formula, what's the main connective? Just let's see in the chat. Contribute to that. Okay, thank you. It's a double arrow. In this second formula, the main connective is the symbol of the tilde. And then in the third case, which one is it there? It's the arrow inside, that's right. It's not the tilde because the tilde is not outside of parentheses. If there were parentheses around this whole expression, then it would be negating the whole thing. But this is just the negation of B, And the negation of B is just the antecedent that's connected to atomic sentence B. Okay, so now up here in the top left, we've got to draw the letters that occur in all of the formulas and in alphabetical order. So what is the alphabetical order of those 3 letters? Yeah, I think I know what it is. But you'll tell me. BJK. Okay, so when you have 3 sentence letters, that requires a total of how many rows yet again? Just trying to drill this procedure, make it as automatic as it can be. It's 8. Okay, and as we know, in the left side, with 8, that means 4 T's and 4 F's below. And then under J, it's 2 by 2, T, T, F, F, T, T, F, F. And then finally here we have T, F, T, F, T, F, all the way down. Single alternating. Okay, so the first part of filling in this truth table now is to just assign the truth value of either T or F to every sentence letter in every row. And as we've learned, there's 2 ways to do that: vertically or horizontally across. So going straight down, every example where we see B is going to be T, 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 F, 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 vertically down. And here's 2 other cases where there's B, so that should be the same. Okay. Now, when we see an example where the letter J is written, it receives the valuation placed here in this vertical column, which, as you can tell, is TTFF, TTFF. So I'm trying to reach this cap if that's okay. One more J here. One thing to say about doing truth tables, by the way, is that when you don't have ledger lines like on lined paper, you have to be pretty careful to make sure that the columns, that the rows are all roughly aligned. I've noticed that sometimes student work can get quite sloppy if you don't take care in doing that. But it's not too hard. Just make sure that they are in the same horizontal line. Now next there's K. There's only one letter here, K, and that's TF, TF going straight down. Okay, so now the easiest part of the truth table is done. From here, we have to fill in under all the connectives, right? So let's start, I guess, over here on the right side. The main connective we save for last, which is the arrow. So we're starting with the tilde symbol. Now, what is the display of 8 things downward underneath that tilde symbol? It's some combination of T's and F's. But what's the order starting at the top and going to the bottom? You could just give me all 8. Anybody who knows that. Underneath tilde to the left of B, the 8 truth values to be written downward going vertically are what? I'm looking at our Zoom chat. Okay, thanks. So 4 F's and 4 T's, because it's the reverse of this, exactly. Now, to complete this part, we have to fill in underneath the arrow in these 8 blank spaces. So what we do is look at the left side underneath the tilde and the right side underneath B. And if you remember the rule is that unless the left says T and the right says F, in all other cases it's true. But in the one case where it's T going to F, left to right, that would make it false. So given that, tell me what the values are going all the way down here, underneath the arrow. Or you can reason backwards. What are the, oh no, better not. Tell me just overall. Good, T, 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 and then F, 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 F. Exactly. Because in the first four spaces, it's f going to t, which is the value of true. But in the bottom four spaces, it's t leading to f, which is the case where the conditional is false. Okay, so now we've finished this part of the truth table related to this formula. Now this one's going to be easy here because it's just a negation of j. So since j says TTFF, TTFF, what are the values to write downward underneath the tilde? And now I'm asking about what to place in these 8 positions starting at the top here, underneath tilde sign. What should it say? And you'll say in the chat, FF, TT, FF, TT. Exactly. You circle that column underneath the main connective, beneath that arrow, and we're 2/3 of the way, but we have to finish this one, which is a little more of a complex expression. So since this is the main connective, we wait for the end to fill in underneath that. So let's do the conjunction within these parentheses first, the consequent or the right-hand biconditional of this. So with conjunction, what's the rule, everyone? A conjunction, an and statement, can only be true when both of the conjuncts are true. Okay, so we need to have 2 t's for this to be a true conjunction. So tell me in these 8 positions, starting at the top, what will be the 8 values to write? Just look at each blank space, see the values on left and right, and tell me whether or not each one's true or false. So we see the first one, true, then false, false, true, false, false, false. And that's what I see here from you, Arlene and Frida. TFF, TFF. Well, hold on. TFFF. TFFF. That's right. T followed by 3 F's, T and then 3 more. Why is it that the first row and the 5th row exhibit the letter T here? Because it's only in those 2 cases where the 2 conjuncts are true. And in every other row, at least one or even both of them are false. Okay, so finally we get to the last column. To fill in underneath this double arrow biconditional symbol, we're looking at the 2 sides underneath B and underneath the conjunction symbol. The rule for biconditional is that the 2 truth values on the left and right must match in order for it to receive T. So with that, let's tell us what are the 8 values to write, going downward, starting at the top row. So help me fill that in. Arlene, looks like you're already there. So true in the first row because T and T. False in the second row because it's TF, not a match. False in the third row because, yet again, no match, TF. False in the 4th row because TF are not matching. In the 5th row, FT, that's also not a match. But in the last 3 rows, FF, 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 that's 3 matching cases, so that's T, T, T. So now we're almost ready to give the answer to the problem. But there's this last step. So simply now I'm asking you, is this set of sentences consistent or not consistent? Yes or no? Are they consistent or not? That's the question about this problem. This is problem, by the way, 3.4.1b. So yeah, question, you have to answer that. Is it consistent or not? Okay, good. Not consistent. Correct. Why is it not consistent? What is it that you're looking at that you're seeing? And by seeing that, you now know that it is not consistent. What is the visual that gives you the correct answer? Good. There is no row where they are all true. Dronreb, let us not be confused. It is no row where they are not all true. If there was a row where they were all false, that still would not be consistency. Because consistency doesn't mean just that they have all F's. It means that there's at least one row where they all say T specifically. So a little more specific. They have to all be T in at least one row for it to be consistent. And we don't see that. Let's go row by row and look underneath the circled columns. Is the first row all true? No, because this one's F. T, F, T. So they're not all true in that row. How about the second row? FFT. Well, only that one's true, and they're not all three true. In the third row, 2 out of 3, TT, but this one's false. In the fourth row, we got this one false and the other two true, so yet again, it's not all true. In the fifth row, FFF, so nothing's true in the fifth row. That's not the case where they're consistent. See, now done red, if you thought that there is a row where they all have the same truth value. It's called row number 5, FFF. But consistency asks the question whether they could all be true in a single possible world. Okay, good. Now, the sixth row, TFF, that's not it. Seventh row, T, here's an F, that's not it either. And then finally, the eighth row, TTF. So we never found one row where they were all true. Okay. Yes, so I see a private question, and the question asks, they don't all have to be the same, just one row has to be all true for it to be consistent. Yes, that's what I'm saying, exactly. So correct. They have to all say the letter T in at least one horizontal row when the table's complete. If you find a row like that, you circle it, and then you say consistent. But when you can't see such a row, then you write the right answer, which is that it's not consistent. Kind of trying to write that on the side here, it's a little bit of a stretch, but this is not consistent. Now, one more quick thing about this here problem. Let me try to show you how a shortened truth table, well, no, never mind. You can't do a shortened truth table when it's not consistent. When it is consistent, you can work backwards from the assumption that there's at least one row where they all are true, and then you can try to just create the one row of the truth table like we did last time. Okay, so that's 3.4.1b. Next up, let's look at question G really fast. Do you see this, the one that I'm highlighting with the cursor? I don't want to create the whole truth table, but I just want to ask you guys just straight off the top. Is G, are these three sentences consistent or no? 3.41G. Okay, good. Lily, you're saying yes. How do you know when we haven't even created the table yet? Well, it's pretty elementary, because those are just 3-sentence letters. And so the top row of the truth table is going to be the row that assigns T to all of them. Since there's no complexity in them, there's certainly a row where they can all receive the truth value true. It's the top row of the truth table. So we know automatically that that's a consistent set of statements. Okay. Well, there's one more truth table analysis method that we have to kind of learn about today. So I'm just skipping to, actually let me go back a bit. Okay, so let us quickly look at, I want to go to the first ones. Let's look at this problem, well, this argument. What you see here is an argument. Now remember, standard form of an argument is that the premises are listed on individual horizontal lines, and then they are separated from the conclusion at the below, and you place like a solid horizontal line in between the set of premises and the conclusion. There's always only one conclusion, it's the bottom line. And this horizontal thing above it is just to show that the things above are all premises and we keep them in separate camps. The premises are on this side of the line and the conclusion is on the bottom side of the line. Here's an argument, 2 premises and this conclusion. Question, is this argument valid? Now, I would love it if one person or anybody could tell me, what is the definition of deductive validity? What does it mean for an argument to be deductively valid? Again, just let's hear that definition in the chat one more time, because it's now coming back to us. What is the definition of deductively valid argument? An argument is deductively valid if and only if what? Just in case, what? What's the requirement to be deductively valid? Just let me know. Because it's fundamental, and we can't ever forget that. Impossible for all the premises to be true and the conclusion false. Exactly. When you have a deductively valid argument, it is not possible for it to have all true premises and a false conclusion. With a valid argument, that combination is impossible. The combination where all premises are true and conclusion is false. So we can use a truth table to determine whether or not an argument is or is not valid. And here's the way of doing that. So take a look at the argument here to the left of the cursor. we'll create a truth table to judge whether this is valid or invalid. So as always, we start with the cross. And we list the premises in the first left positions, and the conclusion of the argument is going to be on the right side at the end of this series. So the first premise, F, if and only if G. F, if and only if G. That's the first premise. The second premise is either F or G. And the conclusion is the conclusion that both F and G. Now, what are the three main connectives? That should be easy because there's only one connective in each formula. So it's double arrow, wedge, and caret or ampersand. Now, to the top left, we place the letters that occur in all the statements in their alphabetic order, which is FG. But so far, nothing I've shown you here is something that's not on the screen. You can see down here at the bottom, I'm trying not to show you the full truth table so that we have some work to do. But that's the top part of the truth table right there. Now, how many rows will this one need? Just a reminder for all of us. We got 2 sentence letters, and so there are 4 rows, correct. Underneath F, we see T, T, F, F. And then G to the right is T, F, T, F. And then, as before, we simply fill in the way that corresponds to the truth value assignment under the letters. Okay, so let's just go through the process of adding the truth value underneath the connectives in each column where there's a main connective. So this is the biconditional. Tell me, what is the truth value here in the first row? True, correct. Row 2, F, that's right. Row 3, F. And finally, row 4. True. Okay, good. Done with that one, circle that one. Now, no mystery here, it's just rules. Why does this say F? Because to the left there's a T and to the right there's an F, they don't match. Why does this say T? Because in this case on the left and right there's both T's and they do match. And also, why does this say T? Because once again we have a match. F matches F, which makes this a true biconditional. Okay. Now we have disjunction, or, and we have to fill in these 4 spaces. So underneath that arrow, row 1, what's the truth value? True. And in the second row, truth value is what? Again, true, correct. Third row, row 3, true, yes. And finally to the last row, row 4. That's the one that's false, yeah. Circle now the second column. So just a reminder about the semantics of disjunctions. Disjunctions or statements like this, they can be true if just one of the 2 things on the left and right has the letter T. That's why this one is true, and so is this one. But when they're both F, a disjunction is false. And that's why in row 4 we see false, but not in the first 3. Okay, now, third sentence in the argument is the conclusion, and it's the conjunction of F and G. So what is row 1 truth value here in that space? True. And then in row 2, F, false. In row 3, also false. And then last, row 4, and that one is also false. Good. So we'll circle this. All right? And now that we have got these 3 circled columns underneath the 3 main connectives, the question is this question. Is there one row in the argument, horizontally, where you see the premises are true and the conclusion is false. In other words, as you scan from left to right through each of the 4 horizontal rows, do you see in the circled area TTF in any of the 4 rows? Do you see that combination? Exactly, Lily. No, the combination doesn't exist. It's not there. We have TTT, but in no other case are the premises both true. So the only one to even really look at is the first one, because it's the only one that's eligible to be invalid, since to be invalid specifically, it has to be every premise is true and the conclusion is false. In this argument, that's not possible. If the premises are true, so is the conclusion, and there's no other situation where the premises are true and the conclusion false. So what that means is, since there's no row to circle, the argument is valid. The argument's valid because it is not possible for it to display all true premises and a false conclusion. So what I've shown you here is how to use a truth table to determine that question and the answer. The same display written on the board is the one that you see here on the screen. TFFT is the first column. TTTF, the second one. TFFF, the third one. But looking at them, no single row displays a combination where the premises are true and the conclusion is false. So let's try another case of an invalid argument, all right? That would be like this one here. So yeah, the first 2, Leo, they are premises. With an argument, let's go back up for a moment. Good question, Leo. You see here, this is the argument that we put into a truth table. 2 premises and the conclusion. How is this the conclusion? Because it's below that horizontal line. So it's easy to spot the conclusion. It's just the bottom. It's the thing underneath a line. And it is always placed on the right of the truth table. And all premises are given in the order they occur to the left. So we start with the first, F double arrow G, the second, F wedge G, and the conclusion there. Is that clear, Leo? I hope so. So yes, the first 2 in this case are premises and the last is the conclusion. Let's take another example to try and work with, all right? Okay, good. So let's look here at this argument. New truth table for the new argument. So here we have another argument. How many premises? There's 2 of them. And we all see the conclusion, right? It is negation D. It is tilde D. It is not the case that D. So here we begin the table in the familiar way by just drawing a cross. And we'll start with the 2 premises, and the conclusion will be placed on the right. So the first premise of the argument is D, if and only if, either not W or G. The second premise is G, if and only if, not D. And then the conclusion is just the negation of D. Tilde D. In other words, not D. Okay, so question. To go further from here, we have to establish these main connective arrows. So 3 main connectives. What are they in each case? What's the main connective of the first premise? Double arrow, yes. It's always the case that if there's connectives in a formula that are inside parentheses, but another one occurring outside, the one that is outside is treated as main connective. Okay. Next, we have the second premise. What's the main connective of premise 2? Premise 2, PR dot 2. Answer for that? Is it displayed? There's a bit of ambiguity because it's the same symbol. Again, yes, double arrow or triple bar. And in the third case, it's almost too obvious to mention, right? It's got to be the tilde because there's only that connective. Okay. So now we've got to generate the sentence letters in the alphabetic order here, which goes in what order? DGW, yeah? And the number of rows you'll tell me is exactly 8. Good. So filling in underneath D, T, 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 F, 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 F. To the right, 2 by 2. T, T, F, F, T, T, F, F. To the next column, it's 1 by 1. T, F, T, F, T, F, and then T, F. So we're on our way, but we have to complete the remaining part of the table. So let's just do, in every situation where we see D, the 4 by 4 display beneath it of T's and F's. Two more examples of D over here. And then this one too, T, T, F, F. Okay. The letter G appears twice, and that is a column that should show 2 by 2 going down. Here's G again, T, T, F, F, T, F, F. All right, and then finally there's W, one appearance of the letter W, and underneath it we'll draw that display TF, TF, TF. Okay, so we will now have to replace or place truth values underneath all the connectives that occur. So let's just begin with this one because it's pretty easy. All we have is a tilde attached to the letter D. And as we've learned, tilde reverses the polarity of D. So a T becomes an F, etc. What then is the downward vertical display underneath the tilde sign here? Good, Amaya, that's right, and Melanie and others. F, 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 F. T, 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 T. Okay, circled this one, and we've got 1/3 of the way there. So working now on this sentence, the main connective is double arrow. So we don't do that until the other parts have been finished first. So that means the next immediate thing to do is this tilde sign. So the tilde is attached to the letter D, and once again, it's going to show the same display as the other tilde attached to D, which, as we've just said, is F, 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 T, T. Sorry, getting a little bit off the ledger. T, T. Okay, and then now for the double arrow here. What you've got to look at are one component on the left, one component on the right, because it's a binary connective. Tilde is an unary connective, so you only have to consider the value of its immediate attached component. But when you have a binary connective, like the arrow, the double arrow, the wedge, or the conjunction sign, you have to look at two things to the left and right. So to the left, it's what's under G. To the right, it's what's underneath tilde. And the truth table rule for double arrow, for biconditional, is when you see a match on the left and right, you write down the letter T under the double arrow. If you don't see a match, it's F. So then just let me know. 8 things to be written here, and we're comparing this with this. So 8 values, what should they show? Yeah, no one's given the answer yet, I think, right? Or, yeah, so yeah, let me know. Okay, so I see you writing F, F, T, 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 F, F. Let's see. So F here, yes, because TF not matching. F here, TF not matching. In the third case, we have T, because F does match F in that third row. Likewise, in the fourth row, F matches F. Fifth row, another match, T and T. Sixth row, T, T, so it's true. And then the last 2 rows, F, T is a mismatch, so that's false. Good. And I think that matches what folks put in our chat, right? So it's F followed by 4 T's, followed by 2f's, right? Okay, now finishing with this. We've got to save that one for last. So next up then, let's do the tilde to the left of W. W shows this display, TF, 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 TF. So tilde on its left is just going to be the reverse. And that should then say what here? If I'm looking at tilde, what shall I write in these 8 positions starting at the top? Pretty, I think, straightforward, but just say one time in the chat. Okay, good, Ethan. F, T, F, T, F, T, and then F, T. Okay, good. Now there's this wedge, and this whole thing has to be completed again before we finish with the main connective. So with wedge, or you're looking at underneath tilde to the left and underneath G on the right. And with wedge, all there has to be is at least one T for this to receive the value true. But 2 F's would lead to it being F, a false. So now in these 8 positions, what are the 8 truth values starting at the top? If you see a T on the left or right at all, it's true case. Okay, so true, true. Here one is false, true, true, true. And then here's one that's false, and then finally at the bottom, true again. Okay, and so that's what I see in the chat, I think, right? So there should be, let's see, 2 instances where it's false. And that's what you have for you to get. The 3rd row and the 7th row. Row 7, row 3. Perfect. Now, underneath this double arrow, the final column to fill in, we compare what's underneath the letter D with what is underneath the wedge on the right, because the wedge is the main connective of this whole right-hand component of the biconditional. So it's a biconditional, which requires that they match, otherwise it's false. So now 8 things. What are those? Starting at the top then. It's a set of T's or F's, and you'll tell me the correct ordering. Okay, Frida, so we've got T, yes. T, T and T matches. This one's F because T and F do not match. The 4th row, a match, so T. The 5th row, it's not a match because F and T don't match. The 6th row, not a match because F and T are different. In the 7th row, F and F do in fact match, so that's true. And then finally in this 8th row, mismatch. F leads to T, which is not matching. So all right, we'll circle this. And we've circled the 3 relevant columns now. And you see the 8 rows displayed in the 3 columns. Question, is this a valid argument or not? Not valid, okay. If it's not valid, then there has to be at least one row that I need to circle. And when I circle that row, what you will see in it is that the premises of the row are true and the conclusion of the row is false. So which row, numbering them starting with 1 at the top and 8 at the bottom, which row or rows is to be circled? You tell me row 4. Okay, good. T, T, F. Yes. That's row 4. And that is the row that demonstrates invalidity. So, correct. The 4th row. True, true, conclusion, false. Since that row exists, it means that in this case, this argument can have true premises and a false conclusion. If it's valid, that's not possible. So when we have a row like that to circle where the premises are true and the conclusion is false, that means that the answer to the problem is that it is an invalid argument. Invalid. This argument is invalid. And let me show you the full truth table in the printed version here of our book. Can we see this clearly? Hopefully so. This is just the larger diagram that corresponds to the same thing that's on the board, just in a printed form. And yeah, you see that 4th row. It's the row where here's the letter T underneath the main connective arrow, 2nd main connective arrow T, but under the conclusion F. All right, so let me also then help you guys with the shortened truth table method that can be used to display invalidity. So when an argument is invalid, one way to show that is what we've done here. Create a full truth table, and then once the whole table has been created, look at it line by line and try and, search for the line where you see T, T, and F. That requires the creation of a whole table. If it's a valid argument, you have to create a whole table also, because validity means that when the whole table is created, there's no existing case of such a line. But when it's invalid, like this one is, you can shortcut and just have a shortened table. So let me try to help you create a shortened truth table for this problem. Okay, so a shortened truth table, let's just make sure everyone's like comprehending this. How many rows are in a shortened truth table? Let me know about that. Just one, exactly. Now, if this argument is invalid, like we've already proven that, but let's just say we didn't prove it yet and we were just curious and we don't know yet. Well, if it's invalid, then what does there have to be in the one row that shows invalidity? What should there be in this, and this space? I should see what order of truth values starting with the first premise and leading to the conclusion. TTF, correct. So we're going to try and work backwards, Lily, from the assumption that such a row exists by just kind of forcing the assumption and saying, yeah, it's invalid because there is such a row, TTF. Sure, that's right there. Now, with the shortened table method, you work backwards from the assumption of the values assigned to each sentence. So this one's easy enough. If this negation is false, if the conclusion is false, then what does D have to be? If tilde D is F, then what is regular D? Have to be. It has to be that it's true, correct. So, because that's the only assigned value that can sustain this result. So D is now known as true, and given that, we place a T under every case where the letter D appears in the overall argument. Okay? Now, since we had to place T here, this tilde is also going to be just like that one and reverse it to F. Now, we're looking here at a biconditional statement. And what we have is that the right-hand term of the biconditional is false. This negation on the right is false. But if the biconditional is true, then what has to be the status of letter G? G, according to logic, and the assumption that this is a true biconditional, and its right term is F, G has to be false. Yes. Because if G is false, and so is this statement, then the required truth value will be established here, T. So since G's now been given the value of F, we place an F under G and every occurrence of G in the rest of the table. So now, we've made an assumption that this biconditional is true. And we've now got the information that the left biconditional term is true. So that means that this symbol here on the right, which is the main connective of the right component, has to show what letter here? Underneath the wedge. It has to be that that shows what? A T or an F under the wedge of the first premise. It has to say T, correct. Because it will have to, in the end, match this for this value to be possible. So if this disjunction is true, but the right disjunct is false, in order for this to maintain its truth, the left disjunct has to be one that's true. So that means that this left formula within this bracket is a true negation. So W, therefore, is a false proposition. And now we have created that table. And look at what row it is. It's the row which assigns to D true, and that assigns to G and W F. And if you look at this full truth table here that is on our screen, you see that that is just the fourth row. And we were able to generate that fourth row starting from the assumption that we could create a truth table where it would present an invalid argument. Okay? So yeah, truth tables can be used in a shortened method when the task is to prove that it's an invalid argument. Yeah, it's only possible to do that, Leo, exactly, when the argument is invalid. When it is valid, that means that no such row exists in the table and it's not possible to create one. So validity requires the creation of a fully completed table in which no row can be circled because no row shows true premises and a false conclusion. The absence of such a row in a full table is what proves validity. The presence of one or more rows in an argument truth table shows that it's invalid. If it's valid, the shortened method won't work. Just like if a set of sentences is inconsistent, then the shortened method will not be possible to show consistency because there just won't exist any such row where all the formulas are true. Okay, so that is the core lesson for today's meeting, just how to do truth tables to evaluate the status of an argument, whether it's valid or invalid. So the only thing remaining to do is to just practice that a little bit more, okay? So let us do that. Let's work on problem A right here and try that one. Okay, so what we're looking at is problem 3.51, question A. And here in the chat, what are the cases in which we would have to show a full table? You have to show a full table when the problem asks, is this a valid or an invalid argument? Use a truth table to prove it. And if the answer is that it is a valid argument, then you have to create a full table. You won't always know whether it's possible to create a shortened table or not until you try it to do so. But when the answer is that it's a valid argument, then you can't have a full table. When do you have to show a full table? When the argument's valid. When the question is this consistent or inconsistent set of statements? Different type of question. If the answer is that it is inconsistent, then you have to create a full table. If the question is this sentence logically true or logically false, or logically indeterminate? To show that it's not logically true, you can have a shortened table. To show that it's not logically false, you can have a shortened table. But if it's logically indeterminate, that requires a full table. So a full table is required when the question is about logical truth, falsity, or indeterminateness, and the answer is that it is indeterminate. A full table is needed when the question is about consistency or inconsistency, and the answer is that it is inconsistent. And a full table is needed when the question is whether the argument is valid or invalid, and the answer happens to be that it is actually valid. So valid, inconsistent, and logically indeterminate, those type of answers all require a complete table. But the contrary of any of those type of answers can be done by means of a shortened table. Okay, because again, a shortened table is just, there's one row that exists that shows it. But when an argument is valid, no such row does exist, so it can't be created. When it's inconsistent, no row exists where they're all true, and so you can't create that row. And when it's not when it's logically indeterminate, you can't, for example, show well, that it's not, if it's logically true, then you can't show that it's not logically true by means of a table that shows one row where there's a false truth value, because no such row exists in that case. Okay, good question. So then here to this problem 3.51a that you see here in the screen share. So this one has got 3 premises and then the conclusion. So let's get them all on the table. So as you know, the way of doing a table for an argument is that the premises are listed first and the conclusion at the end. So left to right, we start with if A, then in that case, both H and J. The second premise, J, if and only if H. The third premise, not J. So therefore, the conclusion, not A. Okay. Top left, display the letters in alphabetical order. How does that go? A, B, C, D, E, F, G, H, I, J. H is before J. So A, H, J. In this table, there's going to have to be 8 rows. Okay. Jessica, I was just explaining that. No, you cannot. Well, oh, sorry. Oh, okay. Misunderstood your question for a half second. Thank you for just asking that question. You can use a full table in all cases if you want to, yes. at a first glance, I thought it said, can we use a shortened table in all cases? No. But yes, you can always use a full table, which will provide the same information and get you to the same answer. In some cases, it might take a little extra work. In general, I think you should probably default to creating a full table, unless you've been instructed by me in the directions. Create a shortened table to show that this argument is, etc. Right? So full table is a safe and sound, tried and true method. But sometimes you can do a shortened table, and if so, I would direct you in a question to do that specifically, so you won't be confused or it won't be ambiguous. Now, 3 sentence letters, 8 rows. Underneath A, T, 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 F, 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 F. Underneath H, T, T, F, F, T, T, F, F. Underneath J, T, F, T, F, T, F, T, F. So when you see the letter A in the truth table, we replicate this ordering underneath it. Here's way over here, the other case where there's A, so T, T. All right. Underneath every occurrence of H, we have that 2 by 2 ordering. And under every occurrence of J, we have that familiar 1 by 1 TF, TF pattern. And one more letter J here. Hey, Peachy. Sorry, girl. I'll be right with you. All right, so yeah, so here to the left of the letter A, and we just had the tilde symbol. I just had to put it in the next room. I'm sorry. Peachy, come on. Come on, kitty. Kitty. Sorry for that, yeah. But so cute. But gotta get this lesson of logic in real fast. Okay, so yeah, to the left of A, the conclusion. Oh, and by the way, this is obviously the main arrow here. It just reverses the polarity of the value underneath A in all 8 cases. So if this was T, 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 F, 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 the negation of that is F, 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 F. T, T, T. Okay, and so this can be circled, and that's at least one column complete. But we have the other 3 premises to still deal with. Now, to the left of J, we have a tilde. And the tilde simply reverses whatever's written under J. And since J goes down in the order TF, 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 tilde just shows FT, and alternating in that order. And we circle that column. All right, now, J just in case H. J if and only if H. Let me know about the 8 values here. Who could just quickly put those in the chat? In the spaces provided here in these 8 areas, what to be written starting at the top, going down underneath the double arrow. You're looking for a match. If you see one, then it gets T. And if you don't, then it gets F. So what do you think about that? T, F, F, T. Those are 2 matching Fs. Another case, 2 matching T's, but then we have some mismatch. F, F, and then the last one is true. And so the order that you have here is T, 2 Fs, 2 T's, 2 Fs, and T. And good, that's what I see here in the chat, and that's correct. We're almost done, but we got to finish off over here on the left. So come on, PG. She just keeps coming back, but that's fine. Conjunction here. And symbol. That needs to have two T's. If it doesn't, even one F is enough for it to be false. So here I have 8 blank spaces. I need 8 truth values. Help me out with that, starting at the top and going down. Underneath the conjunction sign. What do you think? Blank, 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 those spaces there. Who's got it for me? Oh, yes, thanks, Brenna, that's right. And Arlene, I've seen you there too. Exactly, so true in the first case because the conjuncts are both true. But false, false, false. Okay, here they're both true, so that's another one where they're both true. But then we have false, false, false. Yeah. With conjunction, the rule is anything false throws it off and makes it false. So we only have a couple cases where they're both true. The first row and the fifth. Other than that, at least 1 or 2 F's is throwing it off in all the other cases for being true. So now we have this arrow symbol, okay, just the regular arrow sign, if then, the conditional. What's the rule? Well, the rule is that on the left, if it says T, and on the right it says F, then you would write F here. But other than that, you will write T here. Okay, so now tell me about those 8 truth values. Start at the top and then go down, and I'll see what you can get. And we'll complete this truth table and talk a little more about it. So 8 truth values underneath the arrow. What shall they be? So I see Arlene, you're giving T, F, 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 and then 4 T's. So T, F, 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 T, 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 T. Okay, good. And the reason that there's the 3 F's here is because in these 3 rows, 2, 3, and 4, the left side says T, the right side says F. But in every other case, you don't see that. It's either T goes to T, or it starts with F. And in all those cases, there's not that required order to generate F. So now we've reached the end, but we have a question still. Is this valid or is it invalid? Is it valid? Is it not valid? Tell me that information first, whether it's valid or invalid. Okay, so you're saying valid, valid, good. Yeah, and let's see if that's correct. I think it is, because let's go row by row, just to make it very, very clear. What we're looking for now, after we completed the table, is we visually inspect it to see, can we find a row where all the premises of this table are true and the conclusion is false? So is it row 1? No, because in row 1, not all the premises are true. This one is false. So you don't see T, 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 F. That would be the needed truth value display for it to be invalid in at least one row. So row 1 is not the one where all the premises are true and the conclusion is false. What about row 2? Yet again, no, because they don't say T, 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 F. They say F, F, T, F. So the premises are not all true in row 2. If the premises are not all true, then it's not one case where we're showing invalidity. In row 3, well, already we're done because the first premise is not even true in row 3. Same with row 4. Row 5. Okay, in row 5, premise 1, premise 2 is true, but not the third one. And so that doesn't show all premises being true while the conclusion is false either. What about row 6? In row 6, the second premise isn't true, so that's also not a case where all the premises are true and the conclusion is false. Row 7, it's the second premise and the third that are not true there, so we don't see all T's leading to an F. And in the fourth and final row, all the premises are true, yes, but so is the conclusion. So we don't see any row in these 8 horizontal rows where you see the pattern T, 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 F. And since there's no such row, correct. The argument is valid. All right, and just so that we can kind of compare that to the book. So I think this is the better version of it. Yeah, so, sorry, here we go. We can all see this now, right? This is the same truth table printed in a nice typed format here. And it's valid because there was no such row to circle. So that was the correct solution. It just took us a little while to get there. Let me take a look here, see if I can find an invalid argument, and then maybe create a shortened table for that. This part of the problem says like they're all, okay, yeah, so this one maybe will be interesting and useful. Let's try and mess with this one, letter I. And that might be the last problem we practice with today. Okay, so this is problem 3.5.1, letter I. So as we see here, what are the premises? You have, if not F, then not G. I mean, that's equivalent to saying if F, then G, but whatever. So we draw the cross, and first of all, tilde F, then tilde G. If it is not the case that it is not the case that F, then it is not the case that it's not the case that G. And the main connective there is the arrow that to the left and right of which are the two double negations. The second premise is that if not G, then not F. Okay, and then in the conclusion it just says if G, then F. Now, you see the EFG, FG, 2 letters. Now, if we created the full table, we'd have 4 rows, and we can still do that, but let's try the shortened method one time. So who can tell me what would I assume to be the values underneath these 3 arrows? If this was an invalid argument, then I would place blank, blank, blank in the 3 spaces starting on the left, underneath the 3 arrows. It would say TTF, correct. So working backwards from the assumption that this is an invalid argument, we assign that the premises are true and the conclusion false. Now, if that conclusion is false, what do the values of G and F have to be? Because the conclusion is conditional. So yeah, like Leo, it has to be that the antecedent is true and the conclusion false. So G must be true and F must be false. And in accordance with that, we then place those values under every case of G or F consistently throughout. So wherever you see the letter G, it's true. Whenever you see the letter F, it's false. Okay, now, this letter F is false. To its left is a negation sign, a tilde. What goes underneath tilde then here? T, correct. All right. Now this letter G has been claimed as false, so what value is the tilde to its left? Sorry, true. G is true. And so underneath the tilde, we should see the letter F, false. Now, does that sustain the assumed truth value? Yeah, because when the antecedent says F and the consequence says T, that's a case where it's a true conditional because it doesn't display left side T, right side F. Now here, to G. G is true, so what is tilde G? F. If tilde G is F, what is tilde G? So what's the negation of tilde G? T, correct. Over here, same thing. F is false. So what is the opposite of that? True. But what is the opposite of that? Because that is, again, double negated, the F. Now, does this provide the required outcome? Yeah. Because with this conditional sign, we have F leading to T, which is true. And in this conditional, we have F leading to T, also true. But the conclusion is T leading to F, sorry, which is false. So there is a row of the truth table where the premises are true and the conclusion is false. So that means that this argument is what again? The status of this argument, valid or invalid? It is, you'll tell me. It's invalid, yeah. And I think here you'll see as I scroll down on the screen a full truth table which does exhibit this one row in one of the horizontal places. And it's the third row, right? You see there how that third row is the row in the full truth table that corresponds to the shortened table here, which shows the case where the premises are true and the conclusion is false. Also, like FT, it's the third row because the top row in this truth table would be TT, then it would be TF, FT, and then fourth row FF. So, yet again, the shortened method can be used when the answer is that the argument is invalid. There will be one row or more, and by finding those rows, working backwards, you'll be able to prove in a table that it is invalid. Okay. Now, this shortened table method would really come in handy if you had a crazy problem where there were like 4 sentence letters, like this one here. This is problem, let me look up here a bit. What part of the problem set is that? Oh, it's section 3. No, rather, it is section 4 of 3.5. So 3.5.4, problem C, would be extremely complex to do as a full table because this you see are 4 sentence letters. That would require a total of 16 rows. Underneath S, you'd have 8 by 8 T's and F's. Then to the right, 4 by 4, alternating in 4 sequences, 4 T's, 4 F's, 4 T's, 4 F's, and on until you exhausted all of those cases. And you know, it would just create a lot of work. You'd have to fill in painstakingly each line. So here's an invalid argument where that full table wouldn't be needed because you could just work backwards as they've done here. So if this is the argument, and also they added a little extra layer of complexity by getting you to translate the argument from English into this SL translation. So this kind of combines translation and truth table. There could be problems like that that I'll ask you about, like take this English passage, convert it into logic, then use a truth table to tell me whether the argument given is logically valid or invalid. But if these are the 2 premises and this is the conclusion here, then this table, you know, corresponds to the argument. The first premise is a conjunction, the second is also a conjunction, and the third is also a conjunction too. So we would want to assume if this is invalid that this is true, but the conclusion is false. Well, if we assume that the conclusion is false, think about it, it's a false conjunction. And maybe we have options when it comes to that false conjunction. So I mean, it could be false for a number of reasons. One possibility is that it's false because R is false on the right. So assuming that R is false, we then assign that the value throughout. And I mean, that would be sufficient for this one to be false. I guess T, then we have some option. Suppose that we think that T is false and the negation of it is true. Then in this conjunction, you're still going to have one false conjunct and one true one, in which case the overall conjunction is false. Yeah, like I'm looking at this problem, and the only thing about it is that I can sort of sense that there is more than one row in the truth table which displays invalidity. And that's why I think you'll have a little bit of flexibility sometimes in the way that you decide to assign values. Like, so for example, here in this conclusion, you know that it has to turn out to be false in the end. But I guess you could have also made a different assumption that negation of T is false and R is true. And you know, by plugging those in and seeing if it ends up working out consistently, you could see if that different display of truth values would have led to the same result. So yeah, we're running a little short on the time today, but let me just kind of summarize what we've done. We've covered a lot of information on truth tables over the past couple weeks. So first we just showed how to use truth tables to judge whether a single sentence is logically true, logically false, or logically indeterminate. When you do that, you're just looking at the valuation underneath the main connective, and you're seeing, are they all T's, are they all F's, or are they a mixture? If they're all T's, it's logically true, all F's, it's logically false, and if it's a combo of both, it's an indeterminate, logically indeterminate statement. The next thing was, how about using truth tables to determine whether two sentences are equivalent or not? The way of doing that is to place the two sentences in the table, complete the table, and then look through it as you examine to see, is there any row where they don't have the same truth value? Because if they're equivalent, they always have to have the same truth value in every row. But if you find one where one is T and the other is F, or vice versa, then you would circle that row and write, these are not equivalent. If no such row appears where they differ, then the answer is that they are equivalent. Okay, now truth tables can also be used to judge whether sets of sentences are consistent or inconsistent. The definition of consistency is that a set of sentences is consistent when they could all be true at the same time or in the same possible world. So when you complete a truth table for the set of sentences, you then look through it and examine it to see, is there any horizontal row where each of the sentences is true in that row? If one row of that kind exists, you would circle it and you would write that these are consistent. But if no such row exists, then they cannot all be true. And that is when you write not consistent. Okay, and then finally, truth tables today we learned can be used to determine whether an argument is valid or invalid. To do that, you simply take the argument and place its premises and conclusion in the truth table, with the conclusion occurring to the right and the premises listed starting with the first one on the left. You then complete the table, and when the table is finished, you go through it line by line to determine, is there any single row where all premises are true and conclusion false? If you find such a row, you would circle it, and then you would write that this argument is invalid. But if no such row exists, and thus there is nothing to circle, then you simply write valid, because that kind of argument in that case would be one where there's no possibility for the premises to be true and the conclusion false. Okay, so that together with our symbolization work that we've done, like translating just like you did in the last homework, and then basic concepts of logic like validity, soundness, and so forth from the first homework. Those are all the concepts that could be mentioned on the midterm. So I'll send the study guide over the weekend on Friday. I'll have your grades ready for the second homework, and then we'll resume on Monday with the review session over the study guide. And then next Wednesday you can take the exam. So is everything good? Are you guys clear? Are we all right for today's Wednesday meeting? I hope so. If so, then let me know in the chat maybe, and I'll just close for now. I'm going to stop the screen share. All good, everybody? Let me know. I just want to get that feedback from you. See that you're here. Okay, perfect. Thanks so much. So have a great weekend then, and do be in touch with me. Look for my message and notification coming on Friday, or roughly on that day. All right, guys, have a great day then, and see you soon. And to the YouTube crowd, anybody there? A couple of you still? All right, well, have a great one, guys. I'm ending the stream, and you can always come back to it later for your convenience. Okay, thanks.